Good afternoon, evening, morning, wherever you're at, because we're all in different parts of the world. But I am glad that everybody is here today to join us for the next AP Stats CRAM. Today we are going to be taking on the daunting task of covering probability. And there is a lot in this CRAM. There are some things that we're going to go over really quickly. And I promise you we will circle back to a lot of this during the 5-hour CRAM finale in May. I was talking with Sander last week when I was coming up with the presentation, and it is a lot. So we're going to cover that, sort of quickly, and we will definitely circle back to a lot of this. But take advantage of the chat, put questions in the chat to make sure that we're on the same page. Use the Discord channel as well when we're done if you have any questions, and Sander can help you out with that. But for sure, definitely use those options to communicate with us because it is a lot of content. So yeah, we're going to be looking at probability, random variables, and probability distributions, and really just 3 types of those that are the most common on the AP exam. So as always, it's being recorded. I might refer to you in the chat by the name you used on the screen, so just be sure that that's not a problem. All of our socials, of course, check out Fiveable. I'm sure you're taking other AP classes as well, and those have some great resources, not only for AP but other subjects. So coming soon, these are the events coming up for AP Stats CRAM season. Unit 5 CRAM, which is next week. It's one of my favorite units, actually, because it really paves the way for inference, which we all know that is the crux of AP statistics. The Unit 4 trivia, which you also see right above in the little announcements part on the screen, is, I believe, March 23rd is tomorrow night at 9:30. And, of course, the 5-hour CRAM finale. Make sure you join us for that as well. It's going to be a great, busy, awesome day of a lot of stats, and I can't wait. So in this stream, we are going to look at, first of all, the normal distribution, which is sort of covered in Unit 1 of the course exam description. However, it does fall into the probability, so I just saved it for probability. We're going to look at probability with two-way tables. That's a really common thing to come up on the AP exam. We're going to look at independence and mutual exclusivity, which show up on that two-way section. We're going to look at random variables and some kind of rules for those pretty quickly. And then we're going to close out by looking at binomial and geometric random variables. So that is our plan for tonight. And as you can see, like I said, it's a pretty full schedule, so we're going to hop right on in. So probability, really, and I was thinking about this today. I was working in our garden. We've been redoing our kitchen and our garden over spring break. The joys of adulting, right? And as I was working on some of this, I was kind of going through my mind about probability for the stream tonight. And so there's really, probability is the foundation for statistics. They go so much hand in hand, and I didn't realize that even when I took the 2 courses in college, that they go so much hand in hand. Like everything we do in statistics is reliant upon a probability of something happening. So statistics is really just the idea of taking things that have happened in the past or we know have happened and finding the probability of what's going to happen in the future. So it hinges on that idea of probability. So and this sort of timeline, you have a 0% chance, a 1 in 6 chance, which is pretty unlikely to say rolling a 3 on a dice, an even chance flipping a coin, assuming it's fair, drawing a green marble out of a hat when there's 4 out of 5, so that's a pretty likely chance it's going to happen, and then there's the something that it's 100% certain to happen. So that kind of gives you the outlay. Now, one thing about a probability or a proportion, and I always stress this to my students, is that your answer is always going to be between 0 and 1. It could be 0, and that confused some of mine last week. We were doing a inference procedure, and the p-value came out to be 0 exactly. Like I literally created a problem that was pretty much impossible to happen, so we know how that goes. But the probability of it happening was 0, and it threw them off that the p-value was 0. So it could be 0, but it also could be 1, which if inference procedure backwards and flipped your sign in the calculator, it would have given you a p-value of 1. So that's another thing. Either it happens or it doesn't. Those two probabilities are going to always add up to 1. This is like 0 and 1, for instance. Or, 0.75% chance of something happening, or a 0.75 proportion, I guess I should say. Then the proportion of it not happening is 0.25. Those add up to be 1. All right, so again, it is a key part of statistics. We use probability to determine not only how likely something is to happen, but also to predict future outcomes or larger outcomes based on a sample. So if we know the probability of something happening in a sample, then we can figure out the probability of it happening in a population using some rules that we'll eventually get to in the next few weeks. So a very common way, and I know you're all familiar with this, to predict probability in the statistics world is to use a density curve. Somebody throw in the chat, what is the most common density curve that we use in AP statistics? Who can be the first one to get it? Oh, now they're all rolling in. I love the delay with Vimeo. Yes, the normal curve. Everybody's getting it, okay? I imagine that the TikTok fad where you're emailing your professor to ask if they'll bump your grade up or something, and the audio is like typing really fast, and I really, maybe y'all are not as enthusiastic about statistics as I am, but I could imagine that somebody out there was like, I know the answer to this, let me type real fast, and their keyboard is like really loud. That was not my keyboard, by the way. My computer would have freaked out if I was hitting the keyboard like that. That was my desk. So yes, it is. It is the normal distribution, the normal curve, okay? And it's really a beautiful thing in mathematics that this curve can be used to model so many things. And even when it can't be used to model something, we can take a sampling distribution, spoiler alert for next week, that is normal. Based on the central limit theorem or the large counts condition, which is just an amazing thing that works the way it does. And we will look at that next week. So there are many things in the real world that you can model by a normal distribution, such as babies' birth weights. You have some that are really rare, kind of an outlier. And they measure those in percentiles as well, which is the area to the curve equal to or less than a value. So one of my coworkers just had, his wife just had a little baby girl, and I think the weight was like 4 pounds, 14 ounces, which is kind of on the lower end. So I would imagine the percentile there was probably like the 36th percentile. And that means that 36% of all babies born are either equal to 4 pounds, 14 ounces or less. And that's the way they report those numbers to the parents. I remember when my son was born, both of my sons, the big thing that stuck out to me, no pun intended, was my oldest son's head size was the 99th percentile. He's got a very big head, so that always, that sticks out to me. At one point, I think he was in the 100th percentile as he got a little bit older. Big head, little body, So ACT scores are also measured on the normal curve. Blood pressure values, income distribution, all those things are measured with a normal curve, which is really cool that happens that way. So this nice little display here basically captures what amount of, whenever something follows a normal distribution, what amount of data falls within a certain standard deviations of the mean. Does anybody know what the name of the rule is that is displayed here? Somebody want to throw that out for me? The name of the rule. TikTok typing. Yes, it is. It is the empirical rule. That is correct. So the empirical rule states when a distribution is normal, when a set of data follows the normal distribution, that about 68% of the data, we usually round that number down, falls within one standard deviation of the mean. Okay, and then 95% falls within two standard deviations of the mean, which 95% is also a pretty common number we use with confidence intervals. And if we match that up with a two-tailed test, that's a 5.05 significance or an alpha level. So that's kind of important. So 95% within two standard deviations of the mean. And then if you go three standard deviations, that's 99.7%. So basically anything but the outliers, like my son with his really big head. Okay, he's over here in the tail where everybody has smaller heads than him, except for a few select people. So he would have fallen in that past three standard deviations because he was a big time outlier. So that is how the normal curve works, and that comes in handy a lot. Exactly, I see you guys typing it out. The 68, 95, 99.7 rule, that's the same thing, okay? Some people empirical rule, some people just the numbers. It's all good either way. So the area under any density curve is 1. So if I take the area under any density curve, which again, the most common one we use is the normal distribution, we can use the normal curve to calculate a probability of something happening, like those percentiles that we were talking about, to calculate using two methods. Okay, the first method is using a z-score table, and then the second method is using a calculator function. So I'm going to open up a poll just so I can get a good measure of where we're at. Do you use z-score or normal CDF? So answer that question for me so I can get a good handle on where we're at and which way we use. We're going to go over both of them, but I just want to know where we're at. It's hard to know. Okay, cool. It looks like most people use the calculator, but some people do use z-score. And both ways will get you to the same answer, essentially. Maybe a decimal point's a little bit different way down the line, but that doesn't matter. As you all know in AP stats, decimal rounding doesn't really matter. So if you're an AP Cal and AP stats, that drives my students crazy when they take both of them. Because they're like, what do I round to? And I'm like, whatever you want. But what do I round to? And I just tell them 3 decimals. I think that's the AP Cal method, so I've decided to kind of stick with that. So the example we're going to look at is the systolic blood pressure rates for males in the U.S. is normally distributed with a mean of 113.8 and a standard deviation of 10.8. Find the probability that someone has a blood pressure of 125 or higher. So I'm going to give you guys a few seconds, a few minutes to work through that problem, and whichever method you want to do. We're going to go over it both ways. But I'm going to give y'all some time to work through that. So 125 or higher based off of that mean and standard deviation. And I'm going to see if I can pull up my calculator on here. If not, I will go a different route. Don't have it on here. Okay. All right, cool. So let's see what you all have. Chat back up. All right, so this is the way you would do it with using a z-score. What you would do is calculate the z-score by using the formula observed minus expected, or the measure we have minus the mean divided by the standard deviation. That formula is really handy to know, and I'm actually going to type it in the chat because it also works for t-score. Any critical value, that's essentially the formula. And then based off of what type of data you're using, in this case we're using quantitative data, so we're focusing on a mean, not a proportion or a p-hat versus a true population value. All right, so the actual value I would get would be 125, so that's my x, minus my mean, that's what I would expect. That's the average, that's what I would expect, especially when it's a normal curve. The mean is right there in the middle, which is also the mode, and the median. And then I divide by the standard deviation. So that came out to be 11.2 over 10.8. I'm going to make my slides a little bit bigger here. Hopefully that helps you guys to see it some more. All right, so now what we're going to do is we're going to match that z-score on the chart that was given by the formula packet, which if you use the z-score method, you should be familiar with that chart. You match up 1.03, probably 1.0 or 1.03 on the left-hand side, and then across the top find the 3 or the 3.7, and that would give you 0.8508. All right, which in this case, the z-score chart will always tell you the probability to the left. So the probability of 125 or less, which is 8508. That's what the z-score chart will give you. Now, we're looking for the probability of it being higher. Therefore, we need to use the complement. The area of the entire density curve is 1. And then we want the higher portion, which is 0.1492. So the probability of getting a blood pressure of 125 or higher would be about 14.92%, 0.1492. Okay, so that is how you do it with the z-score method. You find the z-score, use your chart. It comes with your formula packet that you'll get the day of the exam. If you're taking the exam digitally, that's something I would print to begin with. All right, so the calculator method. Okay, same problem here. It's really important if you're using the calculator to draw and label your endpoints and your curve. So it really would have been better on this curve to label the mean in the middle at 113.8 with our standard deviations of 10.8 coming out to the right and to the left. Make sure you label that. That's really important. And then you will calculate the area under that curve. Sky, I see your question. Let me pull up a z-score chart real quick. And I can share my screen on that one. Oh, Lord, that's hard to read. ztable.com, how about that? Okay. Give me just a second on that. I know you lost me there for a minute. I'm coming right back, y'all. Window capture. All right, cool. So you get a z-score chart that looks like this on the AP exam. Okay, so our z-score was 1.037. So I'm going to go over here, 1.0, 1.03, which is right here. Okay, 8485. This z-score chart only goes to the 2 decimal places. The one on the AP exam might go to 3. I just, searched for one real quick. So that's where the 8-4 type number came from. It might have been slightly different. I can't remember. I've got a lot of windows open, so I don't exactly remember what that was. So that is the how we got that z-score there. Okay, so we found the z-score using the formula, and then tracked that down and went from there. Okay, and that converted it to a p-value. I'm seeing it in the chat now, catching up. All right, so if we were to do it using the calculator, okay, so back to the calculator method, we would do a normal CDF, all right, which to get that in your calculator, you're going to go second distribute, which is vars, okay, but in blue it says distribute if you're using the TI-84. If you're on a Casio, I'm not really sure, or a TI Inspire, I'm not sure. And then you're going to basically type in 125, that is your lower endpoint. 1 bazillion, whatever number, just essentially infinity in some way, because we want to go all the way to the right. And then our mean was 113.8 from the problem, 10.8 for our standard deviation, and that gives us our final answer. Now, and I wish I could highlight this or would have made this larger in my slides, but I kind of ran out of room. Make sure that you label your calculator speak. Draw a curve. That tells the reader that it's a normal curve, and shading out the area you're looking for, 125 or greater, shows that you understand the problem, and it saves you the trouble of doing the z-score. Then, when you don't just draw this and then write 0.149, you might get credit because they can see it's normal, and maybe you label mean and standard deviation. It's possible. But if you write out the calculator function, normal CDF, label this as lower, label this as upper, label this as mean, label that as standard deviation, you're good to go. All right, everything's fine there. Yes, I see over here in the chat, Sander, 1E negative 99 or 1E positive 99. That is the default that pops up a lot of times. That's totally fine to use. Normally they'll accept anything reasonably above 3 standard deviations or below 3 standard deviations. Priscilla, I would draw the curve as well. You're already kind of taking a shortcut by using the calculator instead of the z-score formula, and I would want the reader to be absolutely sure that you're relaying what you're calculating there. So I would draw the curve and do the normal CDF. You might forget to label, and then the curve might cover you. Okay, you might make a little small error in your calculations, and having the curve gets you an extra point. I think if you do those two things, you're better off doing that. Exactly. I agree with Sandra on that. Okay. So that is normal curve. That's kind of the 2 ways that we can go about doing that. And of course, that is definitely going to build into next week and the week after and the week after and all the way to the end of the year. And most of you, I'm sure, know that. So the next kind of section with 2-way tables that are with probability that I felt we needed to focus on is using 2-way tables. So this is going to be more categorical data. So we had quantitative data, falls onto a density curve like a normal curve. But then we also have 2-variable categorical data. 2-variable quantitative is a scatter plot. And 2-variable categorical, you look at a 2-way table, like something like this, okay? It looks like juniors and seniors at a school were asked which vacation spot they preferred, either the beach or the mountains, and these were the numbers that they got. So from this, you can calculate various probabilities because you have the people in the 11th grade who like the beach or the mountains, and then the total 11th graders, and then you have the same for the 12th graders. Question I want to ask, and I'll give you guys time to answer, is what is the probability of randomly selecting a 12th grader? Those are good points over there in the chat, that the digital exam will not require you to draw. So I would think if you were doing the digital exam and you were using the calculator, maybe you type a sentence out that you're calculating the area under the normal curve from 125 to infinity with a mean of 113.8 and a standard deviation of 10.8. Type out a sentence that covers that calculator speak. And then, like I had on the slide, normal CDF, blah, blah, blah. But just something that the reader knows this is a normal curve, and I'm calculating the probability underneath that curve. All right, so what is the probability based off of our data from the two-way table of selecting a randomly selecting a 12th grader? All right, good deal. I think we've got that. 123 over 287, which comes out to be, going by the majority rules here, about 0.428, which is great. All three of those answers are fantastic that I see in the chat. I really like Dev's answer because it includes context. It's always a great idea anytime in AP Stats to include context in your answer. No bare numbers is one thing I've heard people say. Just giving a number answer is just not a very whole answer. Okay, they really like some sort of context in there somewhere. All right, now the way that I showed context is I put the probability of 12th grade I messed up, didn't I? Ooh, I did. That's a typo. That is bad. Let me fix that. Oh no, y'all are seeing the answers. What was it? 123. All right, cool. Wow, didn't catch that. So 123 out of 287. All right. What is the probability of selecting a 12th grader who prefers the beach? Anika, I think it is a good idea, even when they don't ask for context, to include the context there. It's never going to hurt to put context in your answer. RA context ... unfortunately doesn't qualify as context on the AP exam, but I get what you're saying. That is correct. 100 out of 287. So this probability here in the statistics probability world, I would think of this as an and probability, because we're finding the probability of something happening and something else happening. We want to select a 12th grader and a beach person. So we're looking for the two of them. That means in our two-way table, that's 100 people in our group. And also, we're not changing our denominator because our denominator is a we're not taking a subset of our population here. We're taking the whole thing, okay? We're putting everybody in the basket and pulling one person out, not just taking a subset of our group. All right, now this one's going to change it a little bit. What is the probability of selecting a 12th grader given that they prefer the beach? So answers in the chat on this one. Selecting a 12th grader given that they prefer the beach. So we have a few different answers coming in. Oh, this is interesting here. We got like 2 different answers coming in. Okay. All right, now this one is what's called a conditional probability because there's a condition that's being set. The condition is that they prefer the beach. Okay, so I'm seeing some learning happening. That's really good. I love when I see people type an answer and then say, oh, wait, maybe not. Oh, wait, yes, it is. And kind of bouncing back and forth. That's good. It means you're thinking about it. It means you're figuring out this little bit of content that can be slightly confusing. You're struggling with it. Struggle is a good thing in math, by the way. Sometimes it's not, but most productive struggle is a real thing. It is, so anyways, our condition that we are basing it off of is that they prefer the beach. All right, we are only interested in the beachgoers. So we can take this part of our population from the mountains and we can X them out. They're done. They're done. We are only focusing on the beach people. So now our total is 165. And of course, 100 of them are in the 12th grade. So out of just our beachgoers, 100 of the 165 are in 12th grade. So that condition, this is a conditional probability, is that they prefer the beach. So given that, they prefer the beach. So we want to slim down what comes after that given that part. Another way this could be written would be, of the people who prefer the beach, what is the probability of selecting a 12th grader? Again, it's just a different way of saying we're only interested in that group there. Okay, same problem, and they like to do this on the AP exam. Are the events 12th grade and prefers beach independent? Explain. There's a few ways you could go about doing this. All right, so on this one, and I think we probably, we could go back to our last answers to do this, and a lot of times that's the way the AP exam is laid out. So the probability of selecting a 12th grader is not equal to the probability of selecting a 12th grader just from the beach group. Therefore, those two events are not independent. In this case, I think you are more likely to select a 12th grader from the beach group. So if you just took the 165 beachgoers, the probability of selecting a 12th grader is much higher than the probability of selecting a 12th grader out of all 287 people. So since those two probabilities are not equal, those two events are not independent. Okay, I'm going to type in the chat here a little bit, just something to give you some more ways to check that. The probability of A is given to the probability of A given that B is happening. Okay, that's your check. That's the two probabilities you want to compare. The probability of event A and the probability of event A given that the second event is occurring. You could have narrowed this down and said the probability of selecting a beachgoer is not equal to the probability of selecting a beachgoer given that they're in the 12th grade. So you, instead of slimming down by vacation, you also could have slimmed it down by group and say it's more likely to select a beachgoer out of the seniors than it is the entire school. Therefore, they're not independent. Okay, that one can be really tricky. That's one of those things I would put like on a study sheet as you're getting ready to prepare for the exam a day or two before, and making sure you know that rule for independence. It shows up very often on the AP Stats exam in the free response section, and it definitely pays to know that. All right, so the other example over here is, are the events 11th grade and mountains mutually exclusive? And I'll give you guys a second to think about this, and I'm going to put up a poll, just a simple yes or no. Are they mutually exclusive? So while y'all are thinking about it, All right, mutually exclusive, yes or no? Getting a whole lot of no's. That is good. That is good. Looks like we're all on the same page here. All right. That is correct. So they are not mutually exclusive. And the way that two events are mutually exclusive is if it is impossible for both of them to happen at the same time. And in this case, we do have some 11th graders who prefer the mountains. In fact, we have 99 of them. So if this number is anything but 0, then they are not mutually exclusive. Again, mutually exclusive means that the Venn diagram overlap is non-existent. Okay, so when those Venn diagrams overlap, which they do here with 99 juniors who like the mountains, those two events are not mutually exclusive. Okay, any questions on two-way tables before we move past that into random variables? I'll give you all a second to put those there. I know we just went through a lot. And we will definitely circle back to this in the 5-hour CRAM as well. One thing that I like to do, I'll share this with you in case some people are typing out some questions, with two-way tables is if you end up with a problem that looks like a tree diagram problem. So if we go back to our last slide, let's say that it gave us a percentage of people who were in the 11th grade, and then it gave us a percentage of people who preferred the beach and a percentage of 11th graders who preferred the beach. All right, so basically what it gave us was 164 out of 287, 165 out of 287, and then 65 out of 165 or whatever. I like to take those percentages and simulate with 1,000 people. Okay, and then you make your own two-way table. So filling in the tables, always add a total column and a total row. Sometimes they include those, sometimes they don't. And that makes it easier to calculate both probabilities, whether it's conditional or a marginal probability. Both of those are easier to calculate when you have the total column and the total row. So with the simulating, you can take the percentage, and basically if you simulate it with 1,000 people, 19% becomes 190. And then in that cell, whether it's a total cell or a conditional probability cell, you would write 190, and your total would be 1,000. I wish we had enough time to look at one of those today. We would do that. But yeah, the total column and row is really what's going to be the best thing with filling in the table. And then, you know, if you have 164 and you know this is 65, then you can do 164 minus 65 to get that number. And then you can kind of work around filling in whatever. It's almost like Sudoku. You're filling in whatever sums you can figure out by subtracting. All right, random variables. So there are two types of random variables, one of which we've already talked about. So you have discrete random variables, and then you have continuous random variables, which could take any real number value. That is the normal curve. The normal curve is a continuous random variable. That's the most common one we use in AP Stats, and we looked at that in the beginning. And then you have discrete random variables, which might be something like shoe size. You're either 10, 11, 12. I don't know anybody that wears a size 12.125. That would be really strange. So if we're taking, of course, the mean of a continuous variable is the middle of that normal curve, if we're looking at a normal curve, which we typically are. The mean of a discrete random variable is also known as the expected value. So when you see the word expected value, what is the expected value of event A, event B, whatever it is? Know that is asking you to calculate the mean. What is the average? And again, remember, we go back to that z-score formula, observed minus expected, which is x minus mean, or p hat minus population p. It's that same vocab. Expected value is the mean. The formula for mean and standard deviation of a discrete random variable are given on the formula sheet. We're going to get into a lot of that here in a minute. So the mean, basically you take the amount of the outcome and multiply it times the probability and then add those up. I will show you how to do that. These formulas are really cumbersome, and a calculator is going to be your friend here for sure. So if we have two random variables, make sure I didn't skip a slide. Okay. So if we are combining random variables, and we want to change the mean. So say we have the random variable for class A and for class B, and we want to add those together, or if we just want to take class A and maybe add points to everybody from class A, or multiply by a scalar. Some teachers do that to scale their grades. If you are multiplying or adding, your mean is going to change. The middle of your expected value, the middle of your random variable distribution is going to be affected by a scalar being multiplied or scalar being added. Mean changes no matter what, okay? Also, if you are adding two variables, those two means add up. Mean is easy. It basically changes exactly what you would think. Everybody's score is multiplied by 2. Your mean is multiplied by 2. Everybody's score has 5 points added. 5 points is added to your mean. You're taking class A and class B and combining their averages. You take the mean of A and mean of B, okay? The standard deviation, it is changed by multiplication. Okay, it is not changed with an addition. So if we have a scalar that's being added, standard deviation does not change. It also cannot be added with another standard deviation, and we'll talk about that. There's a special way we have to go about doing that. But both of them multiply. Adding just changes the mean. And then whenever we combine random variable x, random variable y, and we bring them together, then basically when we combine the standard deviations, you need to combine the variances. So you can add the variances, but you cannot add the standard deviation. So that sort of brings us to the Pythagorean theorem of statistics, is what I call it. So you would square the standard deviation of the first random variable, square the standard deviation of the second random variable, add those two sums up, and then take the square root. Okay. I feel like this is a lot. This is definitely something we are going to focus on more on the CRAM. We're just kind of scratching the surface a little bit here. I felt it was more important to talk about two-way tables and normal curve because those are going to show up in the next units. We have to be able to do those to get to the next units. So these are things we're just kind of scratching the surface on, hopefully reminding you a little bit about these things, and we'll dig real deep on that 5-hour CRAM for sure. So one type of random variable, and this one shows up quite a bit, that we might have is a binomial random variable, which has 4 characteristics. In the chat, type one of the 4 characteristics for a binomial random variable. All right, so I see 2 of them. The first one, RA, there is a clear success and failure. That is true. All right, it needs to be very obvious what is true, what is false. Okay, and then, yeah, now we're all kind of rolling in. A fixed number of trials is very important as well. Okay, success and fail rate, that's kind of the same thing with that first thing we were talking about. Trials are independent of one another. So yeah, a lot of people use bins to remember those four conditions. It needs to be binary, meaning it has a clear success and failure. A lot of times people, at least some of my students, come up with this bizarre theory of probability that the probability of anything happening is 50-50 because it either happens or it doesn't. And I'm like, you're totally wrong, but that is sort of leading into binomial because it either happens or it doesn't. There was a question, the one that comes to mind the most for me, it was on an AP exam a few years ago, was the probability of like a rocket crashing. So either it crashes or it doesn't. So that was a clear, that was one way or the other. So yeah, binary, they have to be independent of each other. So the first rocket crashing is not going to affect what happens with the second rocket. A fixed number of trials, meaning we are launching the rocket 15 times exactly. And then the last thing is that all trials have a same probability of success. So probability of rocket A failing is the same probability as rocket B failing. And that sort of ties into independence a little bit, but not. Independence is, does the first one affect the second one? The all trials having the equal probability, which would be the S, the same success, is a little bit different because it may not be affected by the previous rocket, but it is have a different probability, and then that would be, taking rockets from batch A and batch B. They don't really affect each other, but they are different probability of success. Okay, so the example, if I flip a coin 15 times, what are the odds of getting at least 8 heads? Okay, so that's 8 or more. So again, I'm actually going to open up a poll here because there's two ways of calculating this as well. You can use the formula using the binomial coefficient, or you can use a calculator function. So let's see, how would you all go about calculating this problem? Mostly using the calculator, especially for this one. Especially for this one because it is a binomial CDF question. So we are calculating the probability of getting 8 heads, 9 heads, 10 heads, 11 heads, 12 heads, 13, 14, and 15, and then adding all those probabilities together. Because this one, if we got 12 heads, that would satisfy this, okay, because it's at least 8. So what I would do, and then there's your four qualifications for binomial. I'm going to make my slides a little bit bigger to see on these last few. There's a clear success and failure. Either it's heads or it's not. There is an independent number of trials. The coin flip on coin flip 1 is not affecting coin flip 2. There is 15 trials. We're doing it exactly 15 times. That's that fixed number. And they're all equally likely to be heads. They're not changing what they are. Yes, Sky, we will definitely go into combining standard deviations in another session. Sorry, I just clicked back over to the chat. So yeah, so our 4 conditions are met. This is a binomial probability question. So in your calculator, if you were using the calculator function, which I think is easier on this one. Your calculator is always going to, again, just like normal CDF, do the area to the left. And it is going to include whatever value you put in as your endpoint. So we're looking for at least 8. So we want our calculator, since this is a discrete random variable, we want our calculator to do 7 and below. And then we can calculate the complement of that by doing 1 minus. So at least 8. Now some calculators will actually do, will let you put in the lower and upper endpoint. The TI Inspire does. One thing I really like about the TI Inspire. But my TI-84, which is probably the most common one used, you have to, it only will let you do the upper value, and then it just automatically does to the left. So we want to do 7 because it's going to include 7 and everything below it. Our fixed number of trials was 15, and 0.5 was the probability of getting heads. And then I want to find the complement of that, which would be 8 or more. So basically the calculator will only let you do less than or equal to. So we did less than or equal to 7, and then we used the complement to find 8 or greater, if that makes sense. And it actually comes out to be 0.5, which is crazy weird. Didn't expect that to happen, but it kind of makes sense. We're half of our trials, essentially, 8 out of 15, and it's a 50% success rate. So that is one way to do that. If it were saying what is the probability of getting exactly 8 heads, then we would not be doing the complement, and we would do binomial PDF, which is point density function. CDF is cumulative density function, meaning we're adding up a lot of different outcomes. And PDF is where the formula makes a little bit more sense. The formula for this one will be pretty massive, though. All right, the other random variable we have is geometric random variables. Can someone in the chat tell me what is the difference between binomial and geometric? That is exactly right. There is not a fixed number of trials, okay? But usually what that means is that we're going to do something until we succeed. So I'm going to keep doing something until I get a success. Exactly what Priscilla just said. Continuing until you get a successful trial. So in this case, if I flip a coin continuously, what are the odds that my first heads happens exactly on flip number 8? Okay, so that means I'm going to get tails, 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 all the way up to 7 times. And then on my 8th one, I'm going to finally get heads. This is not going to be that obvious. So there is a clear success and failure, so it still follows that. It is independent. It still needs to have the independence. All of them are equally likely to be heads, which is 0.5. It doesn't change somewhere along the way. But instead of having a fixed number of trials, we are going to repeat the event until we do happen to get heads. And it's extremely low. So basically the odds of getting tails, 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 and then heads is less than 1%. So if you use the formula for this, it would be kind of weird with this one. So the probability of getting tails is also 0.5. So it would be 0.5 to the 7th power times the 8th trial, 0.5 to the 1st power. Okay, so the probability of failing to the n-1 power times the probability of succeeding. And that is for a geometric PDF. So this one, it didn't say what are the odds that the first head happens on flip 8 or more. It wouldn't change a whole lot in this case, but it would change some. We're wanting it to happen exactly on number 8. So therefore it is a PDF function there. Okay. All right, so our non-negotiables here, and I know this was a really tough stream to cover everything. I spent more time on the first two. We will definitely circle back to 3, 4, and 5, and I'm already making a mental note of those things that you all were mentioning about combining standard deviations. I know of some AP questions we can go back and look at during that 5-hour CRAM. Let's see, expected value as well, doing it with technology or by doing it by hand if you have a table, okay, probability distribution table. So things you need to know. You need to be able to calculate normal probabilities using your method of choice. If you're using the calculator, label, 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 label. Draw a curve, label, draw a curve, label. Can't stress that enough. That was same for binomial and geometric, if I didn't stress that enough on those last two slides. Be able to interpret a two-way table, also calculate probabilities, conditional probabilities, and determine independence or mutual exclusivity. Independence, the probability of A is equal to the probability of A given that B has occurred. If they're equal, that means they're independent. You're just as likely to have event A happen whether B happens or not, so they're not affecting each other. Mutual exclusivity means that they cannot occur at the same time. So for two events to be mutually exclusive, the two-way table would have to be a 0. Calculating expected values, go back and look at the unit guides that are over here in the chat, or in the, not necessarily in the chat, but over here on the QR code to read over those, and we will definitely circle back to that. Be able to combine random variables and then find probabilities from that. That creates a new normal distribution usually with a new mean and new standard deviation. You can add means. You cannot add standard deviations. Standard deviations only change when you multiply it by a scalar, not adding a scalar. And then the Pythagorean theorem when you have two separate variables that you're combining standard deviations. And also be able to differentiate between geometric and binomial and how to calculate the probabilities from those types of variables. Okay, so again, this is sort of our building blocks for that 5-hour CRAM. And I'm going to go back through probably 10, 15 years of free response questions and make sure there's nothing major that I missed in these 5 non-negotiables from each unit. All right, hop on over to Discord. All right, the voice channel. I'm sure Sandra will be there to take your questions. There might be a lot of questions because there was so much that we covered in kind of a lot of different areas. But I wanted to spend more time on that categorical and quantitative piece that leads into inference, which we get to start next week. Whoop, whoop. Kind of finally getting to the more fun stuff. I say finally, we've only been doing this for like 2 weeks. We've covered so much in a few weeks. All right. Hope you all have a great evening, and if you're on spring break, have a great spring break.